So, very similar to last week, we're going to be going over some practice problems. I want you guys all to follow along, so everyone grab some paper. You guys saw process maps a minute ago. I've printed off a copy of that for each of you. I forgot it on my desk, so Louis went back to grab it. But you will have a process map, because the first thing we'll be doing is looking at where all of our procedures fall in the process map. So does anyone have the notes open? So for the first one, we can take a look. Those of you who have a tablet or something, can you open it to the page with the process map? Okay, so this is actually an example that was in the slides at the very end of the lecture, but we're going to go over in much more detail. So for a GMAW procedure, where we're given the travel speed, the voltage, the current, we want to estimate the approximate thickness of the heat affected zone. And we're going to use an approximate thermal efficiency for an argon CO2 blend. So right off the bat, what do you guys think is the first step? I gave you a very big hint about a minute ago.
Determine the regime.
Exactly. So step one, determine regime. So what's the first number we're going to calculate? D star? Okay, I like that. Now, actually, I think we're going to find, I forgot to give you something to calculate D star, which is we have a plate thickness. So here, our plate thickness is going to be 25 millimeters. So, does anyone have the equation for D star?
D over 2A.
UD over 2 alpha? Yeah, I like that. So, U we have from our procedure D we have is 25 millimeters. Alpha. Does anyone have a rough number of what alpha would be for steel? So this is, alpha is going to be our thermal diffusivity, right? .1. Awesome. And does anyone have units for that?
Meters squared per second.
Perfect. So if you plug in here our travel speed, 0.37 meters per minute, our thickness, 25 millimeters, to what do you guys get?
8.471.
8.471. Did everyone else get that? Maybe? So 8.471 for our thickness, or our dimensionless thickness. Now, what's the second parameter we want for determining where we are in the map?
RY.
RY? Right, the Ricklin number. So, does anyone besides Hero have the formula for the Ricklin number?
QV over 4pi alpha T minus T.
Yep. So, Q we have, U we have, alpha we have, we're going to need K, and we're going to need T minus T naught. Now, in this case, we didn't give you any preheat temperature, so I think it's safe to assume there's no preheat temperature. So we can say T naught is 20 degrees C. What about T? Anyone have a suggestion for the heat affected zone?
718.
718? I like that. Now, this is an example from old exam. If you look at the old exam, you're going to see they use 1045. My guess is, well, actually, in the old exam, they give you some more information. They tell you to use 1045. We can do here with 718. The reality is for the heat affected zone, whichever temperature you use, you're calculating a different region. So we'll do it with 718 here. What about K? Run out of space over here, so I'll come over here. Okay. Anyone tell me what K is? Well, to start with, what is the parameter K? Right. And for steel, what would our thermal conductivity be approximately? $41? Sounds good. And units? Yeah. Okay. So now we have all the information we need to calculate our Ricklin number. So we plug in our Q, which now, this Q. Let's stop for a second here and say, what do you guys think I should plug in for Q? Okay, Eta. Right. So the last parameter we need is thermal efficiency. So it says we want to use an approximate thermal efficiency for an argon CO2 blend. So what would that be for GMAW? This should be in the notes from today. Point 7? Yeah. That sounds good to me. So let's go now. We plug in the numbers, 0.7 times 29.5 volts times 320 amps multiplied by our travel speed, 0.37 meters per minute times, do the conversion right here, and then 4 pi times 41 watts. Perfect. Oh, that's okay. Perfect. So, yeah, absolutely. So I got process maps for all you guys now. So for those of you who don't have it open on your computer, can you pass it down? Can you pass one back? There you go. Oh. There you go. And I'll get you. Pass those back. Perfect. Yep. Oh, sorry. There we go. Has everyone got a process map? Yeah. Perfect. So, if we now put in our alpha, 9.1 times 10 to the negative 6, and our temperature of 718 degrees C, we should get an answer. So, someone who's got a calculator, what do you get? $12.45. Anyone else? Same thing? Okay, so now we've got our Ricklin number and our D star. So, if we go to our process map, where would that put us? Anyone? Sorry? Fast and thick? You guys all agree? Perfect. So, all of the problems we do today, all the problems you're going to see on the final exam, this is going to be the first step. Whenever you have a question where you're trying to calculate heat affected zone or cooling rate or any of the things with those equations you were given today in class, the first step is always going to be to calculate where you are in the process diagram. So this is going to be the most important step. So I want to make sure you guys all understand what we did here. Does anyone have any questions? So, step 2. We're going to calculate the heat affected zone width. So, if we're in the fast and thick regime, on the exam you would have these equations in your formula sheet, but today you guys have them in the class notes. Does anyone have the equation for delta Y heat affected zone for the fast thick regime? Yes, that would be regime 1.
Squirtle.
That sounds right. And probably times something.
T minus melting temperature minus 5.
Right? So, one thing I want to probably clarify then, so when we calculate our heat affected zone, we're doing the melting temperature to the heat affected zone. That's kind of the range of temperatures we're dealing with. So we use 718 here. Probably a better temperature to use would have been somewhere in the middle of 1045, give or take. I think that's what's used on the example from the exam last year. If you're not given a temperature to use, using intermediate temperature or using melting, using heat affected zone, whatever you do use, you always want to say, okay, I'm going to assume this temperature. But typically intermediate temperature works, but you'll see from the process map, if we change our temperature from 718 to 1045, typically that's not going to be a big enough change to put us in a different regime. If you're right on the boundary, then maybe you want to double check that you're using exactly the right kind of moderate temperature. But typically that's something you're not going to have a big concern with. Now, in practice, if you're calculating and you're right on the boundary, you realize these equations are only going to be a little bit of an approximation, because if part of your heat affected zone is in one regime and part of your heat affected zone is the other regime, it's not that the equations are going to be wrong. Like, regimes are still somewhat of an approximate. Like the line you see on the graph here, it's not that you cross that line and suddenly everything dramatically changes, right? You can think there's a point where your approximation with a 3D starts to become less and less valid, and the 2D approximation starts to become more and more valid. But in this case, we're totally fine using 718. We probably would have been just as fine to use the melting temperature, but typically you want to choose an intermediate temperature. So we have this as 718. We have melting temperature for steel. Anyone have an approximate value?
5027.
Sounds good to me. Our intermediate temperature, like I said, is 1045 degrees C. And we now should have everything we need to plug in here and solve. So I'm going to plug that in here, but I want you guys, someone to run this along with me and give me the number. Can everyone still see this here? Is this getting a little bit low? I'll take silence as a yes. You guys all can still see it. 2.9 times 10 to the minus 3. And is that meters? Yeah?
2.90 millimeter.
Right, so same thing. 2.9, that's what I got as well. So 2.9 millimeters. So last step. What do you guys think? Sound reasonable? Maybe? Yes? No? Well, I'd say it's at least the right order of magnitude. We didn't get 2.9 microns. We didn't get 2.9 meters. This was for a fairly thick plate. So this is probably a bead-on plate situation. 2.9 millimeters. Seems not bad. Maybe a little bit smaller than we might expected, but not something crazy. It's reasonable. It's always a good check when you get an answer. Is it reasonable? You don't want to write on an exam and write down 2.9 microns and then submit that and then think, oh, hang on, 2.9 microns. That doesn't sound right. So, does anyone have any questions? Yeah?
If it's a bigger plate, the house is going to be smaller or larger?
In this case, because we're in the 3D regime, thickness doesn't appear anywhere. So if we look at our equation here, where we're calculating heat affected zone, there's no D. Thickness doesn't matter. Once you get into the 3D regime, it's the same for any plate width thickness. You're considering that it's thick enough to be almost infinite. So that's the approximation we end up making. Now, if we were somehow we were in the thin regime, and we had a 25 millimeter thick plate, and we got 2.9 millimeters, we would probably be wondering, because if you're welding through 25 millimeters, so that it's actually considering thin, which means your weld's going all the way through, and your heat affected zone's only 2.9 millimeters wide, I would stop and think, is that likely? Could you weld an inch thick plate with only 3 millimeters of heat affected zone? Maybe if you're doing laser, keyhole, or electron beam or something like that, but typically it wouldn't be that small. But for a thick plate, just a bead on top of the plate, 2.9 millimeters, sounds reasonable. It's nothing crazy. So, I know these are, yep. So TI, this is the intermediate temperature. So in this case, our TI is not exactly halfway between here. I think we're given an equation for calculating TI. We're going to use it the next example. In this case, I should have written it down in the question, but I'll give you TI. This was given on the last year's exam. So TI equals 1045 degrees C. So in this case, it was given. But I think it was, if you look at the formulas that you were given, I know there's a lot of the formulas, there's a lot of numbers in them, but if you look at the formulas given in today's class, there is a way of calculating TI, and it depends on which equation you're using. Yep?
I calculated TI with the equation that I got the exact same number.
You got the exact same number? Right, yeah. So in this case, it was just, for the exam purposes, they weren't going to make you calculate TI. It would have been one extra equation. There was a lot of questions on this exam last year, so I'm sure the people writing it were glad they didn't have to do that extra step. But you guys have all the equations. If you weren't given TI, you'd be given all the equations on your formula sheet. You'd have everything you need to calculate it. So I know it's kind of intimidating going through this whole process. There's a lot of numbers, there's a lot of variables, but really it's just finding the right equation and plugging everything in. If you make your unit conversions at the beginning, which we could have even converted some more units here, we'd have less mess to plug in, and especially because we're using the same numbers a couple times, we could have calculated Q separately and then plug it in each equation. But really, if you just kind of follow along, plug each number in, watch your units, this should be one of the easiest questions on the exam, because all you have to do is grab the equation and plug in the numbers. You had a question?
So E in the equation, is that the constant?
Yes, that's Euler's number. I believe. Someone can double check my naming. It's been a while since I took calculus, but yeah, it's the constant E on your calculator. And I think it might have been mentioned a little bit in class today, but that comes from the derivation of these equations. That is not something you'll be asked to on the exam. You won't be asked to explain where these equations came from to the point of trying to explain why there's an E there, but you will be asked to use them. Has everyone got this? Okay. I'm going to leave this half up for now, and we're going to start with the second example. So if you guys are studying looking at older exams, you're going to see that this has only been taught in the last couple years. 3 years ago, 4 years ago, when I took the welding class, this wasn't taught. So there's only a limited number of practice questions on the exam. So the next one we do, this is a new one. So I would encourage you guys to write it down. This will probably eventually be posted, but it's not going to be on the exam, or it's not going to be in the practice exam questions. So an extra example to study from. So Okay, so I'll give you guys all a chance to copy this down and actually. Everyone's good with us over here? Perfect. So, a little bit different than the first example. Now we're looking at a pipe. So we're given that the pipe has a wall thickness of 11.4 millimeters. We're given the diameter of the pipe. We're given the material and the material properties. Very similar to what we used for steel in the previous example. These are taken for a pipeline steel, which is a low alloy steel, so a little bit of variation, but very similar. And we're asked to estimate the T85 if we're going to make the weld with an SMAW procedure. And for that procedure, we're given the current, the voltage, the travel speed, a preheat temperature, and we're also given a schematic of the joint prep. So, any thoughts on what our first step would be?
Determine the reading.
Exactly. You guys are starting to see these problems have kind of a formula you follow. And if you follow the formula, even if it sounds like a much more complicated problem than the other one, it's going to be exactly the same. So first step, we're going to calculate D star. So here, we're given D, it's 11.4 millimeters. U, we're given in millimeters per minute. Unlike last time, I think we're going to convert this to start with. So U is 349 millimeters per minute times 1 minute, 60 seconds. Whenever someone has that number, just give it to me. And 2 times 5.82. And what does that give us for D star? Awesome. So next step, calculate the Ricklin number, right? So Ry, Q, eta, 4 pi, K, alpha, so, which of these numbers are we missing? We have K, got alpha, we've got U. Let's start with the easy one, eta. We're given that the procedure is an SMAW procedure. So does anyone have today's notes handy? What's our efficiency for SMAW? 0.8. Sounds good to me. Now, what about delta T? So we're given the question, we want to calculate the T85. So our temperature range is going to go from 800 to 500. So we talked about using intermediate temperature. So I'm going to suggest that we use oops. So, really important here. A lot of the problems you have, you're not going to have a preheat temperature. A lot of the older problems if you look at previous exams, but in pipeline welding, it's very uncommon to weld without a preheat. If you're welding on a low alloy steel, especially in Alberta, in winter, likely you're not going to get the cooling rate you want if you choose to weld without a preheat. So in this case, we're given the preheat temperature is 120 degrees C. So when we're calculating our delta T, we take our average temperature, subtract our preheat temperature, and we get our delta T is about, and this, I've got degrees C here, but better would be to write in Kelvin. Did everyone see how we got that?
Where did 250 come from?
Sorry, the 250?
Yeah.
650?
Oh, sorry,
650? So if we're calculating a T85, this is the cooling time from 800 to 500. So if we take the average temperature between 800 and 500, that's going to be 650. So typically, when we're calculating for a range of temperatures, we want to use the average temperature to calculate our parameters to see what regime we're in. So we got one more parameter we're missing here, which is Q. So we were given the voltage, the current, and the travel speed. Anyone have any thoughts on how we would calculate Q from that? Voltage times current. Any other thoughts? No? Well, this is going to give us the right units. We got joules per coulomb, coulombs per second. It's going to give us watts. What else might we not be considering? Well, we have our efficiency in here. We were given something extra in this question. I think we talked at the very end of class, there was a talk about how joint geometry comes into play. So we were given that our joint prep is a 60-degree, I don't know why I put Celsius there, 60-degree angle, not a 6-degree Celsius angle. So I think there was an equation in class where it was Q effective equals Q times 2, let's see. Where in this case, has anyone found that?
Yeah.
Notes today? Yeah? So, what do you guys think? Do you think we have to apply this factor before we calculate the Q? I'm going to suggest no, because right now we don't know what regime we're in. So if we're in regime 2, that factor is probably not going to be important, because if our heat affected zone is so wide that we're out in the region where we're a thin plate, we probably don't have to worry about this should be a relatively small influence compared to the heat affected zone. Now if we're in the thick region, we definitely are going to have to apply this factor. There's really no wrong way to start. in either case, if we use this factor, we get a result which suggests that we should not use it, then we're going to have to double check. So, does that make sense? So if we use this factor, we're kind of assuming that we're in the thick regime. Now if we get a result that says using this factor we're in the thin regime, then we have to not use this factor, go back and double check that result, because it could change. Where if we don't use this factor, we're assuming we're in the thin regime, then if we get a result that says no, we're actually thick, we'd have to go apply this factor, recheck the result. So that'd be iteration. Has anyone come across that before in any other classes? When you get an answer, sometimes your answer makes you question your assumptions, you go back, correct your assumptions, go and do it a second time. So in this case, that's what we're going to do. I'm going to suggest we don't use this factor to start to keep it simple. And if we get a result saying that we are thick, then we're going to apply the factor and rerun the calculation. So if we don't use that factor, we start with we are given our voltage of 21 volts times 140 amps. Does anyone have a number for that works out to? Sorry? 2,914? 40? And I'm assuming that's watts. Did everyone else get that as well? Okay, so now if we plug that in here, times our travel speed we calculated as somewhere. Actually, I don't think I wrote it down here. But we used it up there. 5.82. Our efficiency is 0.8. We're given, so we've been doing everything in millimeters because we were given most of our units in millimeters. So I'm going to suggest we convert our K into 0.050 watts per millimeter Kelvin, just to save us some time. Alpha, 12 millimeters squared per second, and our delta T of 530 Kelvin. So what does that give us?
3.42.
3.42. Everyone else get that as well? Okay, so now, Recolin of 3.42 and a D star of 2.76. What regime are we in? Regime 1? Right. I think we get right on the edge of regime 1. So that means we would be using our 3D fast equations. So what do? Do we stop here and start calculating? No. Because we got 3D fast, we have to correct for the bevel and recheck it to make sure we're still in the same regime. So in this case, if this angle is 60 degrees, that means each of these are also 60 degrees. So our Q effective is going to be Q times 180 degrees over 2 times 60 degrees is Q times 1.5. So we'll say down here, Recolin, we'll just give it a little indication, and we've got a change. This is just going to be 1.5 times the Recolin we calculated before, right? So does anyone have a number for that? I do. (1.5 times 3.42).
5.10.
Yeah, give or take. Now, do we stay in the same regime? You guys look at your map.
Lost empty.
Yeah, so we end up kind of right on the edge. In this case, it's a little bit tricky because we start off in fast and thick. If we apply our bevel correction now, it's suggesting we might just cross that line over to fast and thin. I'm going to suggest that we're close enough to the edge that we can continue to use the fast and thick. Because if we say we're fast and thin, we remove our bevel approximation, it's going to put us back over. We're going to be iterating back and forth all day. So we're right on the edge there. But what that edge is really describing is if we have the 3D equations and the 2D equations, that's where the two of them would predict the same result. So if we're right on the edge, I'm going to suggest we're going to be OK to use our fast and thick approximation. Does everyone agree?
So where do you do this?
Well, so if we were to say, OK, we're on the edge, let's go fast and thin, then in this case, we would say, OK, we shouldn't have used that Q effective. We go back to our original Ricklin number, which is 3.42, and now we're back in fast and thick. So we say, OK, hang on, let's use Q effective. We go back to fast and thin, and we're just going to be iterating back and forth. So because we're on the edge here, really, it's not that one is going to be totally right, one's going to be totally wrong. You could run the equation with both of them, and you're going to find the numbers are pretty close. Now, this is a practical example. These parameters came from, any guesses? You guys have seen me give one of these seminars before. Pipeline welding procedure off the internet. National Energy Board, all companies have to file their procedures. So these came from an actual pipeline that was built in Alberta. These were the parameters. On the exam, we're not going to give you something that's right on the edge where you have to kind of go back and forth and make that decision. But in practice, you guys saw today, all of those procedures from the Lincoln Handbook, a lot of them fall right on that boundary. So it's not uncommon you get these results where you have to make a choice. Are you going to be fast and thick and fast and thin? But the good thing is when you're right on that boundary, typically the difference between the two calculations is not going to be huge. It's not going to be a huge difference where if you use one, you're going to completely right answer or completely wrong answer for the prediction of the T85. And in this case, all we're really looking for is an approximation. Does everyone agree? Does that make sense? Okay, so I'm going to leave this up here, but I'm going to erase our Ricklin and D-star. Go to step 2. So we said we're in the 3D fast regime. Does anyone have the equation for the T85 from the 3D fast regime? Yeah?
How are we supposed to know which formula we can use for T8/5 because we have two formulas, right?
So in your notes?
Yeah, it shows two formulas.
So one should be, is it for one's for regime,
It says like L/A for both of them. So
Not right.
sorry?
Not right.
It says it's not applicable which regime it's for. Like there's just two formulas, but what both of them say, like it doesn't matter which regime.
So the notes have changed a little bit over the years. In this case, does anyone have a copy of the notes? Let's see. This might be new to me. Right, so there's slightly different, ones based on the intermediate temperature and ones based on the just the approximation. In this case, we're going to use this equation. If we were to give you a question on the exam where you had to calculate a T85, it would either be very clear which equation you were going to use, or it would be acceptable to use either one. If we wanted to direct you to use the one with the intermediate temperature, chances are you'd be given an intermediate temperature and say, use this intermediate temperature, or you'd be asked to calculate the intermediate temperature and then use it in the equation. Now, in practice, the reality is there's not really one right or wrong answer. It's two different approaches. They're not going to give you significantly different values, and all of these are really still kind of an approximation. Now, this is a lot better than you can get just by picking a number out of the air, but it's still an approximation. It's not going to be always 100% correct, but it's going to give you a rough idea of what you can expect. I think that new equation with TI, you're not going to see on previous exams formula sheets, because I think that's new this year. But if there was an expectation to use one versus the other, it would be very clear in the exam, use this equation. Okay? So if we plug in numbers here, and I think I erased it, but someone hopefully still has what we had for Q. This was 2940. And hopefully somebody has an answer. Actually, I lied because I'm missing our factor of 3/2 that we added afterwards. So when we first calculated 2940, we were missing that factor for efficiency, so we should have a factor of 1.5 in here.
2.247
2.247?
seconds.
2.24 seconds. Did anyone else get the same?
I got 1.09.
1.09?
I got 2.24.
2.24?
Oh, I did not know.
I got 2.24 as well, so I think. Anyone else get 2.24? So, last step, same as the first question. Does it seem reasonable? 2.2 seconds? It's in the realm of what we'd expect. You look at CCT diagrams in the realm of a couple seconds. Typically, we're probably adding preheat to avoid formation of undesirable microstructures. Now, in this case, we weren't given the composition. We don't know exactly what the steel is. We don't know really what that critical T85 is going to be to form martensite, but 2.2 seconds seems reasonable. It's not a microsecond. It's not an hour. Seems like something you could encounter in welding. So, last question I have before we're done for today. What do you guys think this result would be if we were to use this procedure to do a root pass on a 14 millimeter wall thickness pipe? So, same procedure. Everything the same except the wall thickness is now 14 millimeters. What would you expect the T85 to be? Less? Why?
Because because there's more material for the heat to out.
Maybe.
More, since our QF is changing then, because of the angle?
Same angle, just thicker wall. Everything the same. The angle's the same, all the welding parameters are the same. We're just looking at the root pass, so we're not worried about how much we're filling. Do you guys think this would change? No. If we're in the thick regime, it doesn't matter how thick we are. If you make it thicker, we're still thick. And if you look at your process map, all changing that thickness would make our D star larger, and we'd actually become further away from that line, more into the very definitively thick regime.
I
Yep.
have a question about the calculation.
Yep.
How does the units cancel out? It's meter and millimeters.
Oh, sorry, this should be millimeters. So we converted from 50 watts per meter Kelvin, so this should be 0.050 watts per millimeter Kelvin. Typically, when you're doing a question like this, you can do it in whatever units you prefer. I like to convert everything to a standard system before doing it. So often if you're given numbers in watts and joules, it's nice to just convert to meters. But in this case, because we were given the wall thickness in millimeters, we were given our thermal diffusivity in millimeters squared per second, I converted everything to millimeters. So that's important. If you're thick, even if you make the plate thicker, it's not going to change your result. Now, if you were to use this procedure to weld on a 4 millimeter pipe, then you would have to do everything all over again, make sure that you were in the right regime. So this actually is now probably more information you guys have than a lot of the people who make these procedures. If you go out and you look at a pipeline welding procedure specification, pipeline welding, this is exactly what we just used. This is the WPS, we talked about that, and with the WPS, there are PQRs, right? Procedure qualification records. So if you go into this procedure, which I just got from Googling pipeline welding procedure, you get a procedure qualification record, tells you what parameters are used to make the weld right down here, and these are the exact same parameters we used here. 21 volts, 140 amps, that travel speed. That was the weld they used when they were proving out this procedure. Now, this procedure is qualified to weld on anything from 4 millimeters to 14 millimeters. However, I'm going to tell you guys a secret. It's not because of this. People who make these procedures, they don't necessarily know everything you guys now know. You guys are now a lot smarter than a lot of people who make these procedures, because we're going to talk about codes and standards in a couple weeks. That's what people did when they made this. They made a single weld using parameters they thought or hoped would work, and then they went to the code and said, okay, what kind of pipes we were allowed to weld on? But you guys, if you're working in a code industry, maybe that's what you're going to do. Hopefully you're not going to do that without thinking. But if you work anywhere else and you want to weld something, you don't have someone who's going to give you a manual that says this is exactly how you weld it. If you make a test weld on 11 millimeters, hopefully you guys now know you can calculate approximately what that's going to give you for a cooling rate. You could use what we did before the second midterm. We can convert a cooling rate to a hardness, right? Question 1 on the midterm, cooling rate, hardness, and you can get an idea for what it's going to give you for your properties of your weld. Then if you change to something else, you guys can understand how that's going to change your cooling rate, how that's going to change your hardness, and whether or not you think that's going to be okay. So the knowledge you guys have here doesn't necessarily go into codes. People who write codes write them based on experience, based on knowledge, based on all sorts of things. And we're going to talk more about that later. But if ever you're using something, you guys now have enough information you can think about. You don't have to just believe if the code says I can weld from this thickness to this thickness if I use this thickness to qualify it. You guys hopefully now have enough information you can question that, and even if you end up with the same result, you can think about why you got there and you understand why maybe it makes sense or maybe it doesn't make sense, because the code is not necessarily an instruction book that's going to tell you exactly what to do. You can't do something if the code tells you can't do it, but it doesn't mean that if you only ever follow the code, you're never going to run into problems. There's always going to be some engineering judgment. Yep?
So can you develop a WPS without using a PQR, just using the formula?
For most work, you would still have to prove that whatever you're planning to weld works. Depends on what you're doing it for. Not like if you were to try to just weld something to make a bracket to hold something on the wall in your house. This might be a good approach where you don't have to do any mechanical testing, but you have a reasonable confidence that you're not going to have a bunch of martensite in the random piece of steel you pulled off the shelf to make your hook on the wall. If you were doing it for the purposes of any industrial work, this would certainly help you get in the right ballpark, but you're still probably going to have to prove with mechanical testing that the procedure you've come up with makes a weld that is acceptable. But this sort of information is, if you start with, you're just given, you want to weld an 11.4 millimeter wall thickness, large diameter pipe of that material, and you weren't given the parameters. If you think about all the stuff we've learned in this class now, from deposition rate to the relationship between current and wire feed speed and voltage, you start to realize you guys now actually have enough information. You could figure out for your given steel what kind of hardness you might want. For that hardness, what kind of heat input you might want. For that heat input, what kind of parameters you might want. And get all the way from given something that you could pick up anywhere, what you want to weld, and come up with maybe not a perfect procedure, but certainly a good starting point for how you want to weld it. It's extremely powerful, the equations you're learning here. And these are not equations that necessarily everyone working out industry has. A lot of people who would make a weld on this pipe just know from experience that if they weld with about 140 amps and 20 volts and move so fast, it's going to be okay. And the welder, as he's welding it, knows that if he's welding too slow, it looks like the puddle's about to fall on his feet. And if he's welding too fast, you can see holes in his weld, and he kind of moves at the speed that makes sense for him. But you guys don't have to be there looking at that to know that. You understand the physics, so I wouldn't expect you're always going to get exactly right where you want to be with the first time, but you should get pretty close. And it's certainly going to give you a better starting point than just throwing a dart at a dartboard and guessing what the parameters would be. No questions? Awesome. So these will eventually be posted on the e-class. It might not be till after reading week. If by after reading week they're still not posted, remind me and I'll make sure they get posted up there.